Professor Shlomo Razamat from the Technion, who will talk about generalized lattices and supersymmetric physics across dimensions. Please.
Thank you very much. I would like to thank the organizers for organizing this very, very nice meeting and giving me the opportunity to talk. So I will be speaking about something I will call generalized lattices and supersymmetric physics across dimensions. And it is related in a very direct way, I would say, to the seminal work of Yuval Ne'eman. So again, as we already heard, the big achievement back then was that there were this plethora, big number of particles, a lot of data that were data which was obtained in experiments, and one needed to find some structure in this data. And then the structure emerged by understanding that there is some mathematics behind it, some group theory which saved the day. Okay, so what helped us to classify the particles was the power of group theory, and eventually this led to deeper understanding of physics and emergence of QCD. So the problem I will try to, the program I will try to present here is very, very similar. But instead of looking at a theory which describes our particular nature, we will look at many, many different theories, all the possible universes which can be described by quantum field theories. And we'll try to understand what is the structure of this space of all the possible quantum field theories that we can have. And again, like on the previous slides, when we haven't had an experiment coming from crashing particles together, we here can study various quantum field theories and their properties, relations between them. And in the last 30 years or so, we accumulated a lot of data. There is a lot of data about how these quantum field theories behave, especially in strong coupling regime of these theories. For example, there are various phenomena known as Seiberg dualities or IR dualities. You start from two different conformal field theories. So most of what I'm going to say will be supersymmetric. So there are S's all over the place. So superconformal field theories in the UV, you deform them in some way, and they happen to describe the same physics in the infrared. We know of a lot of examples of these phenomena, but like back then with particles, 30 years ago at least, or 20 years ago, we don't really understand why this phenomena happens. What is the basic mechanism behind this phenomenon? Or if I give you some theory, can you provide me another theory which will be describing the same physics in the infrared? Other phenomena of this type are, for example, emergence of symmetry in the infrared. You can start from a UV theory with some global symmetry. You flow in infrared to infrared, and you find a theory with a bigger global symmetry, a non-trivial symmetry, which is bigger. Again, if there is strong coupling regime in this flow, you flow from UV to the IR, and there is some strong dynamics, we don't really understand. We don't have really a microscopic understanding, typically, of why this happens. Another example is what is called a conformal duality or S-duality, when you have two theories which basically are equivalent. They have a parameter. Both of these theories have parameter or a set of parameters, and you can tune these parameters continuously without generating a renormalization group flow and going from one theory to another theory. Again, we have a lot of examples of this phenomena, but what is the underlying principle? And again, the picture that I will present, similar to what Yuval Ne'eman did many, many years ago, is that behind all of these phenomena, there is group theory. And more generally, there is geometry. Okay? And I will try to explain how this comes about. So I'm going the wrong direction. So let me give you three particular examples of this phenomenon that I mentioned on the previous slide, and then give you the group theoretic and geometric explanation, and also explaining the title of this slide. So kind of the canonical example, the simple example of Seiberg duality, of infrared duality. You start from SU2 SQCD, a supersymmetric version of it with certain number of fields, 6 fields in the fundamental representation. And in the infrared, this theory is described just by gauge invariant objects. So this theory is called S-confining. Another example, so if you wish, this is an example of IR duality. Another example of emergence of symmetry, you start with a very similar theory, SU2, but now with 8 fields in the fundamental representation with some superpotential. These interactions break the symmetry in the UV to SU6 times SU2 times U1. But you analyze this theory in the IR, and because this theory is supersymmetric, we have various tools to analyze this theory. And you find that the global symmetry in the infrared is E6 times U1, a very surprising fact. And here is an example of S-duality, where you have 2 theories, both with SU3 times SU3 gauge groups. Both of them are conformal. There is no flow involved. One has fields in bifundamental, fundamental, and anti-fundamental representation. Another has these types of fields, but also fields in antisymmetric representation. So the matter content is very different, but these 2 theories have an exactly marginal parameter, a coupling which doesn't generate a flow, and these theories are equivalent. And we have gazillions of examples of this sort. So this looks completely random facts in quantum field theory. However, all of these things can be explained geometrically and group theoretically. And the basic idea is, instead of looking on physics in 4 dimensions, you go to physics in higher numbers of dimensions. So all of these facts can be derived by going to a very particular theory in 6 dimensions, taking a supersymmetric theory in 6 dimensions, which has an E8 global symmetry, a very, very special theory in 6 dimensions. And then put this theory on some compact space, a 2-dimensional compact space. When you go to low energy, to energies far below than the scale set by this geometry, you get 4-dimensional theory, and you actually generate the theories that we had on the previous slides. And then various facts about these theories that we have discussed follow from this geometry and group theory. For example, the Seiberg duality, the IR duality between SU2 SQCD and the Vesumino model that I mentioned follows from a very simple group theoretic fact. To obtain these theories, you need to start from a 6-dimensional theory. You put it on 2 punctured spheres. What are punctured is not important. And you turn on flux. Flux is just a configuration you turn on background gauge fields for the global symmetry, for the E8 global symmetry, which breaks the E8 symmetry down to E7 times U1. And you can do group theoretically this in 2 different ways. So these are 2 octets of fluxes which are equivalent inside the E8. They look different, but they are equivalent. And because these things are equivalent in the theory you start with, the theories you will obtain in 4 dimensions should be exactly the same. And this is an explanation of this fact from group theory. Not really a microscopic explanation, but an explanation from group theory. The theory that we claimed has E6 times U1 symmetry in the infrared, you actually obtain by compactifying the same theory on a torus with flux again, which breaks the symmetry from E8 to E6 times U1, and that's why we see that symmetry. As dualities are usually related to various pairs of Pan's decompositions of surfaces, which are equivalent. Surfaces, they change, you can continuously deform them from one to another, and in 4 dimensions, this manifests itself as duality. So there are these complicated effects in 4 dimensions, which are become just geometric and group theoretic facts once you enlarge your scope or your viewpoint. So the basic idea of our modern understanding of these facts, of where they come from, and again, it's like Yuval Ne'eman's work. It's not, we don't know the quarks yet, but we know the group theory that is behind all of these effects. There is an organizing principle. An organizing principle is to go higher in dimensions and compactify and look on group theoretic and geometric equivalences between things. So here is a picture which comes with it. So what we usually do, we start from physics in 6 dimensions. In some sense, once you go into higher and higher dimensions, we have less and less quantum field theories, so conformal quantum field theories that we know about. So we start from 6 dimensions, and I will mention on the next slide, this is the highest number of dimensions where we know of non-trivial conformal field theories. And then we play these games. We compactify the 6-dimension theories down to lower dimensions in all possible ways. And this is given by choosing geometry and choosing some group theoretic information. And from these games, we can reproduce a huge variety of facts that we know in lower dimensions. Not everything. There are corners, there are some types of facts that resist still our embedding into this geometric picture, but a lot of things we can understand. Okay, and the fact that we know about these theories in 6 dimensions, in fact, in 5 dimensions, is because there is this octopus, which is beyond what I'm going to talk about, which is M theory and string theory. Using this more abstract or geometric and like description of quantum field theories using M theory, we can deduce existence of these theories in 6 and 5 dimensions. And given these theories, we can understand facts in lower dimensions. So our understanding at the moment flows this direction. We start from 6 dimensions or from string theory, and then we can derive, by using simple methods, physics in lower dimensions. However, a thing that I already mentioned, as we go up in dimensions, the theories become more complicated. We only can really understand them by embedding them in string theory or in M theory. So for example, we do not have a Lagrangian description, really, of conformal field theories in 5 and 6 dimensions. In dimensions smaller or equal to 4, it is easy to construct theories with Lagrangian. We have a lot of such theories. Our standard model is such a theory. In 5 and 6 dimensions, really we are sure that non-trivial conformal field theories exist because of string theory constructions. And in fact, we only know of supersymmetric conformal field theories. So, for example, there is a question whether non-supersymmetric conformal field theories exist at all in dimensions, in these dimensions, in 5 and 6. In number of dimensions which is bigger than 6, we know that superconformal field theories do not exist. It is a mathematical fact. And again, we don't know about CFTs in general. Okay? So basic questions we want to ask is whether we can find some some field theoretic construction of higher dimensional conformal field theories which will not rely on string theory or M theory constructions. Even in lower dimensions, to construct quantum field theories, Lagrangians for quantum field theories, we need to give up symmetry. This is, again, the notion of emergence, which we already heard about in this meeting. So if you want to construct a theory with given properties, often you cannot impose these properties on the Lagrangian. These properties often just emerge in the low energy. So what can happen when we go to higher energy? Maybe even space-time symmetries should emerge, and we should not make them manifest in our description. Okay, so this is the basic idea of this program and what we want to do. And here is kind of, again, the depiction of this idea going backwards from the picture that we had. So again, before we claimed that we understood a lot of information starting from higher dimensional theories and going to lower dimensions. Now what we want to do, we have this information. We now understand a lot of physics using group theoretic facts and various things in the lower dimensions, dimension 4, 3, and 2, and so on. And now what we want to do, we want to harness this information. We want to use this information to reconstruct physics in higher dimensions. So this is not a new idea. It appeared in different fields of physics, and it goes under different names of the constructions in high energy physics, or wire constructions in condensed matter physics. And of course, there is the idea of holography, which one would want to take all of the reconstructing complicated theories just from quantum field theories also to theories with gravity. And I think Ofer will talk about that after me. Okay, so So this is the summary of what I said on the previous slide. So we understand in many cases a lot of compactifications of higher dimensional CFTs to lower dimensions. We want to try to reconstruct the higher dimensional theories from this data, for example, as certain limits of compactifications. Say, looking on compactifications from 6 dimensions to down to 4 dimensions on very large Riemann surfaces. When we perform compactification, we lose information about the theory we started with. We lose data. But maybe if we look on all the possible compactification, we can retain enough data to reconstruct the original theory. And the more concrete idea is to study lattices of conformal field theories. Okay? So we are very familiar with lattice constructions of quantum field theories starting from quantum mechanics. We start from a quantum mechanical model with degrees of freedom labeled by some special lattice. And then we're taking various limits, which often are called continuum limits, to go and construct continuum quantum field theories. So an idea, a constructive idea, is to start from lattices of CFTs, of lattices of theories in higher than 0 + 1 dimensions, and taking various limits. For example, in some cases, maybe we will expect to obtain continuum theories, say, in 5 and 6 dimensions by starting with these lattices, but we are pretty sure that we should not get anything in dimensions higher than 6. So what is the mechanism? What goes wrong in this, or what will go wrong in these constructions when we try to construct these higher dimensional theories? So here is another picture. So this is the familiar story, for example, when we start from, say, the standard model from QED, and then we engineer a certain system of atoms, which we can effectively describe by some spin interactions, quantum mechanical system with spins, and then we take certain continuum limit of that system to produce quantum field theories, continuum quantum field theories in some other dimensions. For example, in 2 dimensions, that 2-dimensional CFT is not the same as the theory we started with. This is some machine to produce interesting physics from a single theory of nature that we have, which is the standard model, but to construct a lot of different effective field theory descriptions in various limits. And this is the idea of the construction, where you start from a theory which in M-theory language lives on M5 branes. It is a 2,0 theory. In modern language, you compactify it on a certain torus with certain data. In 4 dimensions, you obtain some gauge theory with a lot of SUN gauge groups. And then you take some double scaling limits, when you take the number of these gauge group to be very large, and you turn on some vacuum expectation values. And in this particular case, the claim is that you recover the same theory you started with. So this limit of taking a lot of gauge groups kind of blows up the torus, and you recover the original theory on a finite size torus. Okay, but we will want to understand these constructions in wide generality. And again, the idea is really goes back to Phil Anderson, that more is different. We start with lower dimensional CFTs. We take a lot of them, we couple them together, and the hope is to produce higher dimensional theories, which we cannot produce otherwise. And again, the important thing of going to the lattices is that once we are with these lattice pictures, part of space-time symmetry is lost. Okay, we have the lattice. Really, the UV description has a lattice. We don't have translational symmetries, and we will want to recover them only in certain limits of the construction. So in the last 6 minutes or so, I will tell you about some baby steps in trying to understand this direction. So we understand a lot going from 6 dimensions to lower dimensions, and now we would want to go from lower dimensions to higher dimensions by studying lattices of conformal field theories. So the first thing that we would want to understand about such theories are the symmetries of these theories. Okay? Again, going back to Yuval Ne'eman's seminal work, symmetry will play a crucial role, eventually we expect. So for example, what we can do, we can study conformal field theories. With supersymmetry,
it's easy to construct conformal field theories which have exactly marginal deformations. There are tunable parameters and that we can play with. Okay, there is no renormalization group flow involved. The space of couplings is often called the conformal manifold. Here is an example of such a lattice. You take some CFTs and you couple them with some superpotential interaction. So these operators are some chiral operators in the CFT. You couple these theories together. Each theory, for example, has some global symmetry, and this interaction breaks the global symmetry to some diagonal subgroup. Now I will mention two trivial, almost trivial facts about such constructions, which are I find nevertheless interesting. So for example, in the model that we had before we couple different theories together, we have a copy of conserved current for a global symmetry for each copy of the theory we start with. Once we couple the theories together, then these symmetries are broken to a diagonal group or diagonal subgroup. And we can write the non-conservation equation for the symmetries which were preserved before we couple the theories together in such a way. Again, there is some supersymmetric magic going into writing precise equations like that. So the equation there is the supersymmetric version of current conservation for these theories. Now, if we massage a little bit this equation looks like this non-conservation equation looks like an equation as a conservation equation for some current where we add components of currents for the discretized dimensions. These operators appearing here are some chiral operators which are marginal operators. So there is some natural candidate for a conserved current in one more dimension here. And we can have a hope of taking certain limit and producing something interesting in the continuum, or maybe not. Another thing I want to mention here is that, of course, we can construct the charge operator for the global symmetry. So the charge operator, since we broke into a diagonal subgroup, will be a sum over charges for all the symmetries coming from all the copies. In this lattice language, we're integrating a current over the space and summing over the discretized direction of space. What we can do also, we can construct a quantity where we integrate over full space-time instead of space and summing over the discretized directions, but we don't sum over the lattice points. Okay, this happens to be a marginal operator, which in certain sense is exactly marginal and is independent of this position on the lattice I that we fix. Okay, so in that sense, this looks like a defect operator for the symmetry that we have in the problem. And it is a sort of a topological operator. And this connects to a very large theme in contemporary research of understanding symmetries in more generality as topological operators. So the way we define symmetries now is by looking on all the possible topological operators that we have in quantum field theory. So this is a very simple illustration of that. If we have a usual charge, it is integration over a current over some spatial slice. And the fact that it is conserved means that we can move this slice. In fact, we can change the shape of that slice also. And now that we understand that really the geometry behind the conserved currents are these topological operators, we can ask various questions of looking on topological operators which are not codimension one, which are higher codimension, looking for other more sophisticated structures like giving up unitarity of symmetry generators and so on, what is now called a non-invertible symmetry, which is really a tension between locality and unitarity. And we can ask these questions also for lattice models that we have. So in the last minute of my talk, here let me connect this discussion to the discussion we had in the beginning of reducing from 6 dimensions down to 4 dimensions. So if you just look on these lattice constructions of CFTs, this discussion might look as very artificial. But in fact, once you go back and understand and look at what you get when you compactify 6-dimensional theories down to 4 dimensions, it is very common that you will obtain quantum field theories in 4 dimensions or in lower dimensions, which are lattices of exactly the sort that we have discussed. Okay, so you start from a theory in 6 dimensions, you compactify it, for example, on genus G surface. So there is a Riemann surface associated to the theory. It doesn't look like a lattice. But Riemann surface you can deform continuously. Okay? So the idea is that there is a continuous deformation of this Riemann surface, which will give you a lattice-like structure. In field theory, these continuous deformations correspond to tuning some continuous parameters, some couplings of the theories. So there are some subspaces of the conformal manifolds of this theory where the theory actually looks like gluing together basic building blocks. Okay? And then the idea is to take various limits of such lattices, where you have large lattices, you tune maybe couplings to special values, and asking the question, what would you obtain in such limits? So maybe you will obtain a continuous theory, maybe you will not obtain a continuous theory. I don't know what you will get, but this is an interesting question to ask. So let me summarize. I'm dead the 3rd time today. So we understand a lot of lower dimensional physics geometrically by embedding it into flows across dimensions, starting with higher dimensional CFTs. However, higher dimensional CFTs themselves are very mysterious beasts from field theoretical point of view, okay? And we would want to understand them better. So an interesting question is whether these higher dimensional beasts can be engineered in lower dimensions by giving up symmetries. And more generally, studying these lattices of CFTs might lead to interesting understandings in physics. Thank you.
Since time is short, we have time for one question from people who didn't ask questions, like Eliezer. Microphone, please, is coming.
Ignore your preamble, Marek. My question is, there are 2 questions which are related. Do you think you should assign some symmetry, a residual symmetry, to the lattice with which you start? Because you just speak on a lattice without giving it a characterization. So question number 1, is there some residual symmetry? And question number 2, can you envisage this in a more dynamical fashion? Namely, could there be a breaking symmetry in that theory you don't know to write in a higher dimension, which would lead you to this solidification in the lower dimension?
So let me understand the first question. You want, like you're asking, what are the symmetries that we preserve on the lattice? Or?
Yes.
Yes.
Not the gauge symmetries, the space-time symmetries.
Yes, so when you tune, so you go on this conformal manifold and you can tune on general locus of conformal manifold, the only symmetry you preserve is the symmetry which is preserved by the interactions. You read it off from like what is not broken by anomalies or not broken by superpotentials. But on special loci on these conformal manifolds, some new symmetries emerge, for example, translation symmetry. So in this lattice that we had, if we tune, like I didn't specify it, but there are a lot of couplings, exactly marginal couplings, we can tune them all, and if we tune them all to be equal, there is a translation symmetry. And like the defect operator that I mentioned is related actually to that translation symmetry. You can use the translation symmetry to translate it on the lattice, for example. Okay?
And what would define the lattice spacing?
Okay, the value of the couplings. Okay, so that is, I don't have a very good, like there is no scale, but what defines the couplings is, what defines the effective distance between CFTs is the value of the coupling. And here there is an interesting point that like on a usual lattice, we usually would go, like when we take a continuum limit, we take some distance to be very, very small. But in these supersymmetric constructions, when you tune the couplings to some value, there is an action of S-duality. So in some sense, if you go beyond certain value of the coupling, like effectively, the two CFTs become like larger away from, like farther away from each other. So a continuum limit probably would correspond to tuning these couplings not to 0 or to infinity, but to some special loci, like to self-dual loci in some sense. So about the second question, you're asking whether there are some T symmetries that can emerge that are not explained from higher dimensions. Yes, there are such examples, but they are in the realm of random facts that we know and we cannot explain. My guess is that all of these things also should be explained, but what we were trying to do till now is to explain everything starting from CFTs in 6 dimensions. But to explain this residual accidents or random facts, probably you will need to go one step farther to string theory or to M theory. Okay, so not everything I expect will be explained by this construction, and there might be things which just happen, and that's it.
Thank you very much.